Here we go, another video on hypothesis testing. This time we're going to perform hypothesis testing on two means, or two different populations. We're going to use the calculator to do it. Up to now, when we've done the hypothesis testing of means, it's been with just a single mean. Now we're going to, as I said, compare two different populations here. All right. Okay, so as you guys know, I like to start off with the conditions necessary to perform a test. Well, whenever we're going to to conduct a hypothesis test for two population means, the first thing we actually have to do is to determine if the data sets, the samples that we're given, if they're independent or dependent of each other. Okay, so for this video, we're going to focus on just independent samples. I'll make another video where we do the dependent samples. So if we have independent samples, what that means is that one sample has no effect, or it doesn't have the same amount of things in it, or the same things in it as another sample. For instance, if we're interested in comparing mean salaries of engineers in Dallas, Texas to the mean salary of engineers in, let's say, New York, well, we're looking at different engineers, right? We're looking at different people, because the people in Dallas aren't necessarily the same people that are working in New York. So those will be independent samples. On the other hand, dependent samples will be a situation where, let's say, we are part of a trial. We're trying to see if this new pill that comes on the market, if it actually helps you lose weight. So what do the companies do? They do clinical trials. What they do is they take a person or a group of people, they weigh them before they take their weight loss pill, and then they weigh them sometime afterwards. In this case, you have the same people in both samples. That's actually a case of dependent samples, which we will cover in a later video. All right, so when it comes to how to do a two-mean hypothesis test for independent samples, we're going to have two options. I'll come to the conditions in a second. You're going to use something either called a two-sample z-test, or you're going to use something in the calculator called a two-sample t-test. Okay, well, what's the difference? Well, the difference between z and t is always the same. The difference is, do you know your population standard deviations or not? If the population standard deviations are known, then we are doing a two-sample z-test. If instead the population standard deviations are unknown, that's when we're going to do a two-sample t-test. Okay? Once again, it's the population standard deviation that makes the difference here. And similar to the one sample variant of this, remember for the one sample z-test, the one sample t-test, we need n to either be bigger than 30 or we need it to have a normal distribution. Here we go. Same conditions. We need our sample sizes to either be both bigger than 30, or if they're not large enough, then we have to have a normal distribution for the population. So the conditions are still the same. All right. Let's get straight into a question here. Here we go. So Amelia repairs smartphones, and she claims that phones from two major brands, A and B, have a different number of broken screens per week. Based on her historic data and repair receipts, Amelia finds that the population standard deviation of broken screens for brand A is 4.5 screens a week. She finds the population standard deviation of broken screens for brand B is 3 screens a week. She randomly examines receipts from 50 different repairs of each brand. Okay, so our sample size is 50. That's bigger than 30. We don't have to worry about a normal distribution. The results from these samples are shown in the table below. Is there sufficient evidence at the 0.05 level of significance to conclude that the phones from the two brands have a different number of broken screens? Okay, so a lot to unpack here. First of all, we're looking at two different brands of phones. We're having, let's say, Apple versus Android, something to that effect. Well, those are independent samples because they're not the same phone. So we are going to do either a 2-sample Z or a 2-sample T. But because we have a population standard deviation, that means we're going to do the 2-sample Z test. All right. And of course, before we even get to that, we always have to start with constructing our hypotheses. So we are trying to test if the mean broken screens is different between the two brands. Do they have a different number of broken screens? So when you're dealing with two means, this is what your hypotheses will look like. We are going to have mu1 and we're going to compare that to mu2. What does that mean? We are going to compare the average number, the mean number of screens from brand A. We're going to compare that to the mean number of screens from brand B. Excuse me. So subscript 1 will represent brand A. Subscript 2 will represent brand B. You notice for hypotheses with two means, we no longer have a number in the hypothesis. So we're trying to see if mu1 is different than mu2. That means we're testing, is mu1 not equal to mu2? That is our claim, which is the alternative hypothesis. The null hypothesis is a scenario where mu1 equals mu2. All right. So because we have two samples, they're independent, and we have a population standard deviation, we are going to do a 2-sample Z test. So the 2 means 2-sample. 2-sample means 2 samples, and Z test because we have population standard deviations. Well, how do we get there? Well, all your hypothesis tests are located in the same place. We're going to hit Stat, go to the test menu, and number 3 is your 2-sample Z test. Okay. The question becomes, do we have the data or the statistics? Well, if you go back to the question, for us to have the data, we have to have all, remember there's 50 different repairs for each brand. We have to have all 50 of each brand in a different list. We don't have that information, so what we have are the statistics. So we're going to go over to Stats. Okay. And here we go. I will actually write down this stuff. So sigma 1 and sigma 2. So remember, anything with a subscript 1, brand A, subscript 2, brand B. So sigma 1 is the population standard deviation for brand A. Okay, what did they tell us? They told us that the population standard deviation for broken screens for brand A is 4.5. So sigma 1 is 4.5. Sigma 2 is the population standard deviation for brand B. And they tell us that standard deviation is 3 screens per week. Okay. We're going to need the X1 bar. That's the sample mean for the brand A. That's 5. And now I'm looking in the table here. And N1 is 50. From that same table, we see that X2 bar is 3 and N2 is 50. Okay, so we are going to now input all this information into our calculator. Okay, so here we go. I'm going to try to memorize this. Sigma 1, that was 4.5. Sigma 2, be careful here, that was 3. Okay. X1 bar, that's going to be 5. N1's 50. X2 bar, that was 3. And N2 is 50. Okay. Hey, at the bottom, it's our good old friend. What tail test do we do? Is this a two-tail, left tail, or right tail test? This is a two-tailed test. Two-tail test. So we select the not equals 2 option. Okay, we go down to calculate. And we are looking for our p-value. Okay, if you're asked to calculate the test statistic, it would be the 2.615. But our p-value to 3 decimal places is a 0.009. P-value is a 0.009, which means we're ready for our decision. We take our p-value, compare it to the alpha, the level of significance, which was a 0.05. Add an extra 0 for easier comparison. 9 is less than 50, so we're in a scenario where the p-value is less than alpha, which indicates we should reject the null hypothesis. So yes, the number of broken screens, so we're saying HA is true basically. Yes, the number of broken screens is different between the two brands. Therefore, our conclusion is there is enough evidence to support that claim. Okay. All right, see if we can sneak in one more. A fish hatchery, a biologist, at a fish hatchery, a biologist claims that more red than silver salmon have hatched. Okay, to test this, she counts the number of baby salmon swimming out of the hatchery into the stream over a 2-hour period. She counts on average 57 red salmon an hour over the 2 hours, with a standard deviation of 13 fish. Okay. And 62 salmon, silver salmon, an hour over 2 hours with a standard deviation of 25 fish in the 2-hour period. Assume the population variances of the two types of salmon are not equal and that the number of each type of salmon is normally distributed. Okay. At the 0.05 level of significance, is there sufficient evidence to conclude that there are more red than silver salmon that have hatched? So once again, a lot to unpack here. Okay, but let's start with our hypothesis. It's always a great place to start. It's the place you have to start. So we're going to let the red salmon represent, have a subscript 1. I can write better than that. Sorry. Red represents 1. Silver represents 2. So come over here to the last sentence. Is there sufficient evidence to conclude that there are more reds than silver salmon? So we're trying to determine if mu1, the mean amount of red salmon, is more than the average amount, the mean amount of silver salmon. So mu1 is greater than mu2. This is what we're testing. This is our alternative hypothesis. The null hypothesis, on the other hand, is mu1 just equals mu2. Okay? All right. So now we need to start thinking what type of test do we need to perform. So we have 2 samples. They're independent, right? We can't have both red and silver salmon, right? So they're 2 separate groups, 2 separate samples, independent. So it's either going to be a 2 sample Z or a 2 sample T. Well, the difference is the population standard deviation. So yes, it is true that they give us a standard deviation here, but you have to use your context clues. That standard deviation is actually a sample standard deviation, because that standard deviation of 13 fish came from when she took her sample of the 57 red salmon over a period of 2 hours. So this is actually a sample standard deviation, which means we do not know the population standard deviation. So because the population, specifically the population standard deviation, is unknown, for this we have to use a 2 sample t-test. Okay. All right. So where is your 2 sample t-test in your calculator? Well, it's right underneath the 2 sample z. Stat, test, Two sample t is number 4. Okay, and you can see there's some values that we need, an x1 bar, a s1, and an n1. So let's go ahead and grab these from the problem. Okay. All right, x1 bar. Let me do a different color. X1 bar is the mean amount, the sample mean amount of what color salmon? Should be the red salmon. So X1 bar is the mean amount of red salmon. She counts on average, okay, I'm right here. She counts on at an average of 57 red salmon an hour over 2 hours. So the mean number of red salmon is 57. X1 bar is 57. Okay. S1. S1 is your sample standard deviation. Okay. And let me go back to the hypothesis test. So I skipped over this point, but hopefully you know our input, we have the statistics. We don't have the actual data. All we have are the statistics. Okay. Because remember, data means that you have the information in a list somewhere. We do not have that. Okay, S1 is the sample standard deviation for the red salmon, and that is going to be 13. And here's a little tricky part, N1. N1 is the total number of red salmon that she looks at over this 2-hour period. Well, it says that she counts an average of 57 red salmon an hour for 2 hours. So she's out there for 2 hours. She's counting 57 salmon every hour for 2 hours. Our N1 is going to be 57 times 2. There. So 57 times 2 gives us, that should be 114. Okay, 57 times 2 is 114. So once again, it's 57 salmon per hour for 2 hours. That's how we get a total of 114 red salmon. Okay, now let's switch over to silver salmon. X2 bar. This is the average number or the mean amount of salmon she sees, silver salmon. She says that she sees 62 silver salmon an hour over 2 hours. 62 silver salmon an hour over 2 hours. So X2 bar is 62. S2, that's our sample standard deviation for the silver salmon. Say that 5 times fast. It's 25. And our N2 will be the 62 fish that she's seeing per hour times with the standard deviation 25 fish in the 2 hour period. So she was staying there for 2 hours again. So 62 times 2, that should give us, let's calculate that. That should give us 124. Okay. Now all we have to do is feed all of this information into our 2-sample t-test. 2-sample t-test. Because the population standard deviations are unknown. Okay, stat, test. I'll go back. All right, 2-sample t-test, number 4. As I said, the input is stats. X1 bar, that was 57. SX1, that's the sample standard deviation for the red salmon. It was 13. N1 was 114, I believe. X2 bar, 62. S2 is 25. Our N2 is 124. And here we go, y'all. Something new here. Oh, not yet. And then what type of test is this? We are going to do a right tail test because our HA is a greater than. Right tail test. Select that, go down. And there is now and it's only for a 2-sample t-test, do we have this new option we have to select called pooled. This is how you know whether or not pooled should be yes or no. Maybe we should write this down. If population variances are equal, then we are going to select yes for the pooled option. Okay. Otherwise, meaning if the population variances are not equal, then we're going to select no for pool. Okay, so that's what pooled is, and I won't get into the deep details about it, but look, what's going to happen is they're going to give you a statement, a sentence. Right here. Assume that the population variances of the two types of salmon are not equal. Okay? And that the number of each type of salmon is normally distributed. Well, we don't have to worry about normal distribution. But anyways, the population variances are not equal. Therefore, for pooled, for this one, we're going to select no. Pooled for this example will be no. Are not equal. So no. So for pooled, we're going to select no. All right, let's calculate this thing. We work this out and we see that we get actually a p-value of 0.974. So remember, a p-value goes between 0 and 1. If you ever get a weird number like 6.52, keep on looking. You're going to see an e to the negative number. That means it's a small p-value, okay? So you'll never have a p-value greater than 1. You'll never have a p-value less than 0. So our p-value is a 0.974. Okay. To quickly finish this up, you know the drill. We take the p-value, compare it to alpha. I'm assuming alpha is 5%. It's always 5%. 974 is greater than 50, so our p-value is greater than alpha, which means we're going to fail to reject the null hypothesis, which means our conclusion is there is not enough evidence to support the claim. So no, we don't have enough evidence to say that there are more red salmon in this river than the silver salmon. All right, y'all. See you in the next video.